Okay, so the term called breaking Exadata, which of course is done for dramatic effect. Okay, I suppose a slightly more reasonable or slightly fairer title would be reminding you that everything you hear from the marketing team is not necessarily the whole truth. Right? This is more a question of not trusting everything you hear and remembering that sometimes Exadata is just a very big piece of hardware, and that's the only advantage you get from it. Okay. And what are the circumstances? This is really what are the circumstances in which that is true. And we'll start just by a quick run through of the unique selling points for Exadata. You've got storage indexes, which are a big thing. They're actually a little bit unstable, by the way, but they can give you a tremendous benefit. You can't control them though, and that's a bit sad. You have the smart scan and the offload, the thing which says we can do table scans really, really, really quickly for all sorts of reasons, and one of the reasons being sometimes you just don't do the work if you can possibly avoid it. One of the reasons being that actually, and the way the marketing puts it, the hardware identifies the rows that you want. Or you have the smart flash cache. Well, cache is cache is cache. Putting a little bit of sensible choice into it is, well, heck, Oracle's been doing that with the buffer cache. Where they do it is interesting. And then there's hybrid columnar compression. How do you scan through 45 billion rows in 15 seconds? Well, you squeeze 45 billion rows down into a lot less, right? Make it a lot smaller, and the stuff you don't want disappears faster. But these are the sort of big four labels that Oracle gives us about why Exadata is so incredibly good. So, Smart Scan and Offload, just a quick run through here. If you look at the Exadata database machine, what you've got is sort of a replication of this type of hardware. We have a few nodes, which are the database nodes, the things which do the intelligent work. We've got memory, we've got database instances. You perhaps have an ASM instance, not necessarily in the latest version of Oracle, but every node has an ASM instance. We have memory, we have local disk drives, if nothing else. We have some very fast CPUs. So we have a small number of machines, nodes on our system, which are database servers. And then we have the cell servers or the storage servers, the name's sort of more or less interchangeable. What you've got down there is just essentially a very, very stripped down version of the Oracle kernel. And basically all it can do is talk to another Oracle kernel and read disks, right? But it's essentially a piece of the Oracle kernel, but stripped and optimized for various activities. This is the place where your disks are, this is the place where your data is. And the key feature then with the cell servers, some of your bits, your nodes, are just the cell servers. This is where your data resides. These are the instances which talk directly to the data. The database instances actually communicate through a network to the cell server instances. And the network is unbalanced. We only talk from top to bottom. We do not talk sideways. So it's not a everyone talks to everyone data network. That's the picture. So when we run a query, the database server that's running that query for you, a single instance, a single session, is able to say, well, partly because I talk to ASM, partly because ASM talks to the disk down the bottom, if I want an item of data, I know which of these cell servers down the bottom will hold that item of data. So I can send a message, I can decompose the query if necessary, I can send a message down to the appropriate machines down the bottom here to say, I want this block which you are looking after in your local piece of hardware. Local disks, you can access them much faster than you can network disks, right? That's winning point number one for Exadata. Disk access is local, it's not across the network, right? That's an important hardware win, okay? If you want to make your databases go faster, right, don't use a SAN. Stick a load of disks in the server. Easy, right? It's hardware, nothing clever, okay? So, coming back to the USP bits, why does that particular picture make Exadata so very fast? What does Oracle tell you Exadata can do really quickly, right? Bloody great table scans. Absolutely. Why not? What have we got from our various features there? The cell servers. One serial execution at the top says, well, you know, I've got 8, 10, 12 cell servers down the bottom. You think I'm running a serial query? I've got a dozen machines down the bottom there. I'm running parallel. I'm not telling you, I'm pretending to be serial. I'm running parallel. I've got 12 other Oracle instances running statements, table scans for me. Right? So your query is automatically parallel. Be careful that you don't run too many parallel queries at the database server end, otherwise you run into parallel contention down at the disk end of it. What about the storage indexes? Storage is broken up into megabyte chunks. When Oracle says, I've decomposed the query, the cell servers are running it, it can pass the predicates down to the instances which are on the cell servers. And we've got the storage index, so actually the cell server can say, hey, before I read this megabyte you asked for in a table scan, I can actually just check my little storage index and say, well, there's not going to be any data there. So I don't read it. I just send a message straight back saying I don't need it. Right? Works with table scans. Local memory, the smart flash cache. If the cell servers can see what you're asking for, it starts caching what you're going to be asking for. So even if it turns out you need to read that megabyte, there's a fair chance, if it's a popular megabyte, it will be in the cache. And so you get quicker. What else? We only send the useful columns. Right? If we're doing smart scans, Oracle says, yeah, okay, you want this megabyte, but actually you only want rows which match this condition, and you only want these 5 columns. So what goes over the network isn't a megabyte of Oracle blocks, it's the smallest amount of data which the database server really wants. Minimize the network traffic. Right? How do you minimize the network traffic? Put local disks into your servers. Don't buy Exadata. Okay? Minimize the network traffic. Oh, and of course, yes, hybrid columnar compression. You squeeze big amounts of data into a small amount of space. So that 1 megabyte can contain a huge amount of data. Right? So if you actually physically hit the disk, there's an awful lot more there than what appears to be a megabyte's worth of data. So these are the reasons why very, very big table scans can be very, very quick. 1, we don't actually scan them. 2, we only pick the bits we really, really, really want. And 3, we maybe squeeze these things down to very tiny physical objects, which we expand out, pick the bits we want, and send a small packet up the network. Okay, so how do we break it? Well, very few people run queries which just say, do a table scan of 1 table. We often do joins between 2 tables or more tables, right? But if you do a very big hash join, what happens? Oracle says, well, okay, this chunk goes in memory, I scan this chunk, I can do the 2 scans hit very quickly, build in memory, scan through here, do my join. And what if it says, yeah, but this thing won't fit in memory? Bang, we flood it down to disk. As we scan the second one, we do part join and flood down to disk, right? So what happens? You get a very, very fast table scan, you get effectively, relatively speaking, a slow flood down to disk. What have you flooded to disk? Something which you want the whole of, you get a slow read back. Right? You start doing big hash joins, you don't get any benefits of Smart Scan, you get full-size I/O. So I have seen a system where Oracle says, okay, we've got a 4 terabyte table scan here, bloody hell it's quick. Oh, we're doing a hash join, and I have to dump 600 gigabytes to disk. And dumping 600 gigabytes and reading back 600 gigabytes is 8 times as slow on that machine as table scanning 4 terabytes. Because the whole lot goes down to disk, the whole lot gets read back, there's no clever tricks that cuts down the workload. Right? So big hash joins, multi-table hash joins, parallel hash joins, read my blog about parallel hash joins, you can get massive floods to disk. Oh, and parallel hash joins, right? The business of pushing predicates down to the disk is very confused and very delayed if you do the wrong type of parallel hash join. So you actually read a lot more than you wanted, and you write it down, and you read a lot more than you wanted, and you write, and so on. So hash joins are a threat, right? It isn't just simple table scans. ETL, right? ETL processes, what do you do with those very often? Well, you take a very large table with a larger number of columns and you flood it down to disk, and then you do things with it. But what's the problem with that? Very often, as you're going through your big massaging process, you are not selective about which rows you're interested in, you are not selective about which columns you're interested in. So all the clever tricks of saying, yes, we scanned it, but we only picked out a little bit of it, so the network traffic is very low, just doesn't apply. Or, well, it doesn't always apply. You get caught, this is the trap that you get caught in. You don't get the selectivity. What about compression? My tables are huge, let's compress them before I dump them to disk to do my processing. Well, we read a megabyte, right? We have compression units. We've packed what was 40 megabytes of data into a 1 megabyte chunk. Fantastic. So what happens? we get a query which says, give me that megabyte, and down at the cell server, Oracle says, okay, I will expand my 1 megabyte. Oh dear, it's bigger than a megabyte. I've spent a load of CPU expanding it. It's too big because I'm only allowed to send a megabyte packet, so I can't send you the data you wanted. I'll have to send you the megabyte packet, and the database server expands the megabyte packet. So you spend a lot of CPU compressing it to write it down here, and when you query it, you spend CPU down here to expand it, throw it away, send the packet, expand it again, expending CPU on the database server, where you've only got a few of them, right? Rather than 14 of these down here, where it doesn't matter if you waste a bit, you re-expand it. You do decompression twice, right? So ETL, be very careful. Big hash joins, be very careful, because you do things which are more complicated than just select a small number of rows and columns from one table using a table scan. That's breaking Exadata. Okay, thank you very much. I have to cut that one down to 5 minutes for open world.